Hi, ladies and gentlemen. The next portion of our modern physics unit is about pair production. And let's quickly review what are some ways that photons can interact with matter. We've previously spoken about the photoelectric effect, where a low energy photon knocks an electron out. Okay. We've also spoken about the Bohr model and the atomic energy levels, which also deals with low energy photons knock an electron to another energy level. Okay. And we also spoke about Compton scattering, where a medium energy photon knocks an electron out and loses some of its momentum. Okay. Now, what we're going to talk about today is the fourth way, which is about pair production. So we take a quick look at this video over here. Okay. So in Compton effect, we notice that an electron is knocked out, and the photon that was going in this direction had lower energy and a higher wavelength as it knocked out the electron. With the photoelectric effect, we see that the electron gets struck and it fully absorbs the low energy photon and escapes. In pair production, notice is a little different. The photon strikes the nucleus, which then gives off a pair of particles. Okay? It's a very special pair of particles. Let's just watch that one more time. Okay? So in pair production, the photon knocks into the nucleus and actually turns into a pair of molecules. So pair production is the energy of the photon is directly converted into two particles. In fact, they're two special particles. They turn into a beta particle, a beta positive, and a beta negative particle. In other words, it turns into an electron and a positron. A positron is just a certain type of antimatter. Antimatter, which we're going to discuss more later, simply means that it's the same as an electron, same mass, but it has the opposite charge. Okay, that's what antimatter is. So in the example that we saw, we had a high energy photon, a gamma ray actually, hit the nucleus. Now the nucleus is just there just to help with conservation momentum, but the energy over here for HF completely disappears and turns into mass of a positron and the mass of the electron. Okay, meaning that the E of the photon literally turns into M1 plus M2. So the question really is, how much energy do you need to turn a photon into 2 electrons? Well, if we take a look at this diagram now over here, let's actually calculate it out. We know that the mass of electron is 9.11 times 10 to the negative 31 kilograms. And the positron, because it's an antiparticle of the electron, means it has the exact same mass. So overall, if I want to figure out how much energy a photon needs, okay, we're going to go to Einstein's formula of E equals to mc squared. So in this direct conversion of energy into mass, we know that it's going to create 2 times 9.11 times 10 to the negative 31 kilograms of mass times the speed of light squared. So this energy that's needed is equal to 1.64 times 10 to the negative 13 joules. So that's how much energy that photon originally had. If I wanted to figure out the frequency of that photon, I could always then set this formula, this energy, equal to hf. We would use the joules version of h. So F would equal to the energy divided by h, which would equal to 7 times 10 to the 20th hertz, 2.47 times 10 to the 20th hertz. So this is gamma radiation. Okay, so basically the energy of the photon turns directly into the mass of both an electron and a positron. Another possibility is when you have 2 gamma rays actually coming together and they strike. Okay, and when they strike, they produce the electron and the positron here. So in this case over here, it's really the same question as before, but just understanding that each photon is going to turn into each particle. So when I want to find out how much energy that one photon needs, or each photon needs when they strike each other, we will end up with E equals to mc squared again, except we'll just be dealing with the mass of 1 electron at a time. In order to solve for the energy and then the frequency. Okay, so this is another example of pair production. Now, in both cases, you have to understand that there's several conservation laws that are considered here. The first one is that there is going to be conservation of momentum and energy. Okay, the fact is, it's easy to see the conservation of momentum with the 2 photons, because when they strike each other, and we have the 2 electrons going out, the momentum in equals the momentum out, which is 0 in both cases. Now, the reason that the other case works, which is the very first one, over here, there's going to be conservation of momentum and energy, because that nucleus is so large that when you have something with a small momentum strike it, that nucleus will move a teeny little bit, but most of the momentum of the photon gets turned into the positron and the electron itself. So there's still conservation of momentum and energy in this example over here. There's also going to be conservation of charge. Okay, the fact is the electron is negative and the positron is positive. They have the same exact charge, but they're just opposite signs, which means that they still cancel out to be 0, which is what the charge of the photon was. Okay, so now let's talk more about antimatter itself. As I had previously stated, antimatter is matter with the same mass and opposite charge.
Forms intense electrical field. Electrons within this field become accelerated upward. Above the storm, where the air is thin, the electrons can ramp up to speeds nearly as fast as the speed of light. When these ultra-fast electrons encounter an atom, they emit gamma rays. Very rarely, one of these gamma ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron.
Okay, so basically this video is talking about how antimatter is created on Earth all the time, every time in fact that there's a thunderstorm. And we have detectors out in space that detect the presence of these antiparticles, or antimatter particles. So notice every particle has an antimatter equivalent. An electron has a positron or an anti-electron, proton has an antiproton, and neutrino has an antineutrino. But it's not even just the fact that the proton itself is just an opposite proton. There are three quarks that make up a proton, and these are the up, and down quark. But in an antiproton, there's actually an anti-up. Now we represent antimatter with a bar over it, an anti-up, and an anti-down. So it's not just the fact that it just has an opposite charge for some certain reason, but it literally has all its constituents, all its parts are completely the opposite of matter. But what's interesting, though, is when matter meets its exact antimatter equivalent, they destroy each other and they blow up and turn back into pure energy. Okay? So when matter meets its exact antimatter equivalent, they annihilate each other and turn into pure energy. So the fact is, if that electron and positron struck each other again, they blow up, and you create this. You create photons, according to, of course, E equals mc squared. So if we had that electron traveling along, and it strikes that positron traveling along, okay, they blow up, and you create one photon going one way and one photon going the other way. Okay, there has to be a production of two photons because of conservation of momentum. Okay, so the fact is, when an electron and a positron meet each other, they're always going to annihilate each other. When an antiproton and a proton meet each other, they're going to annihilate each other as well. And they turn into a whole bunch of different particles, but mostly gamma radiation. Okay, so understand that these particles, are very difficult to capture, because anytime they interact with its exact opposite, they blow up. In this case, we just show again our proton and our antiproton annihilating each other and turning into gamma radiation here. Okay, and notice there's always going to be conservation of momentum. Now, the reason this is especially important is to understand what we currently use for energy today. Currently, what we use for energy today is chemical reactions, whenever we have rocket fuel. And the thing is, though, no matter how powerful this rocket fuel is, the efficiency of rocket fuel is about 0.0001%, meaning the rest of it is waste product. Okay, I'm not saying that rock fuel isn't powerful, but it doesn't give us very much options in terms of storage space. There's just too much stuff, which is why a lot of people are now researching nuclear fusion instead, which is what the sun uses. But the problem with nuclear fusion, which is, let's see, about 6,000 times more efficient than chemical reactions, is that, well, 6,000 times 0.0001 is still 0.6%. Efficient. There's still a lot of waste product, even though it's a lot cleaner than nuclear fission would be. Which is why if you talk about antimatter, and we talk about interstellar travel, even traveling to the different stars, scientists ultimately are hoping to create antimatter engines where you have almost 100% conversion of mass into energy every time a particle meets its antiparticle. Okay, but the thing is, there's not very much antimatter in existence, which confuses a lot of scientists, because whenever there's a reaction, we notice that there's always equal production of matter and antimatter. Every time two photons collide, there's always antimatter being created. So, and the thing is, what we should be seeing is that there should be an equal amount of matter and antimatter filling the universe. And there would constantly be explosions whenever they meet up, but then there will always be recreation of them every time the photons strike each other. But instead, what we actually do see is that the universe is 99.9999999% matter, and a very little bit of antimatter, which is created all the time, but then disappears every time it interacts with matter. And we're not really sure why that actually is.